Welcome to Data Science 1, Probability, Counting Methods 2, Permutations. From the last few videos, we've seen that counting is really important. We looked at the multiplication rule, which says if we have two events, E1, or experiments, E1 and E2, that can occur in N1 and N2 ways respectively, then the combined experiment can occur in N1 times N2 ways. We also looked at sampling with replacement. An outcome can appear more than once in a combined experiment. Sampling without replacement, an outcome can only appear once in the combined experiment. And if you don't know these ideas, go back and look at the last video. Okay, so when you think of permutation, think of the word ordering. So we're interested in counting the number of ways we can order or permute a set of objects. This is naturally sampling without replacement, because once an object is placed in an ordering, it cannot be placed in a different position. So this leads to the idea of what's called a factorial. Suppose we have n objects to order, and by using the multiplication rule, we have this idea of n and then this exclamation mark, which is factorial. So it's how many choices do I have for the first object if I have n of them? Well, there's n of them. But once I've placed that first object, I only have n minus 1 left that I can place. And the same as n minus 2 left that I can place. All the way down until I place the very last one. And that last one, I don't have any choice because it's only one left over. So this exclamation mark is called the factorial operator. Hence, n factorial reads as n factorial. N exclamation mark reads as n factorial. Let's look at an example. At a ceremony, there will be 7 speeches given. How many possible orderings of the speeches are there? Well, we have n speeches. So for the first one, I have 7 options. Once that one's placed, I have 6 options. 5, 4, 3, 2, 1, and that's it. But we would write this as 7 factorial, which is equal to 5,040. So there are 5,040 possible orderings of the speeches. And notice, again, we could do this without listing them out, which is the whole point of having these counting rules. Here's another one. Let's extend the previous example. Suppose you're a speaker at the ceremony. How many ways can you be the third speaker? Okay, well, for the first person, well, you're not the first person, so there's only 6 people. Okay, and then once we pick that person, well, now there's only 5 left because you're just not the third person. There's only one way to choose that third speaker, and that's you. Okay? And then the fourth speaker, there are 4 ways left, 3, 2, 1, which is 6 factorial, or 720. Hence, there are 720 ways that you could be the third speaker. If we wanted to know the probability that you are the third speaker, then we can consider the event E, that you are the third speaker. If we look at the probability and we use this equally likely idea that you're equally likely to be at any space in that ordering, then there are 6 factorial over 7 factorial, 720 over 5,040, or 1/7, which kind of makes sense, right? Where should I put you? Any one of the 7 slots, 1 out of 7. So things do make sense. Okay, suppose we don't want to order all of the objects. So, for example, at the last minute, the ceremony can only have 3 speakers. Okay, something came up, people can't make it, or maybe something really good happened and they need to shorten it down because they want to do this other event. So, how many ways could we have 3 speakers? Well, there are 7 times 6 times 5, and then the rest of you just don't get to go, or 210 ways to do this. So in general, the way you can think about this is we just go down to k minus 1, or n minus k plus 1. Now, if you write this out, this is the factorial in the numerator divided by n minus k factorial in the denominator. So we've had n factorial over n minus k factorial. That's called n permute k. So I have n objects, of which I'm going to permute k of them. So it's how many orderings of n objects do I have when I'm only going to put k of them down. I'm not going to use all of them. All right, so here's a simple idea. A bakery sells 14 different types of bread, and in their window they have 4 bins to put the bread on display. Okay, so I've got 14 to start with, And I'm only going to put down 4 because that's all I have space for. So how many ways can they position the bread in the window? Well, this is going to be n permute k. N here is 14, permute 4. So 14 factorial over 14 minus 4, quantity factorial, is 14 factorial divided by 10 factorial, which is 14 times 13 times 12 times 11, which is 24,024. Hence, there are 24,024 different possible displays for that window, with only using 14 different types of bread to begin with. So think about that. That's a lot of ways you can organize that. Okay, so this has been really quick, but hopefully the idea is getting to you that you need to know how to count. And this just takes practice of looking at these different types of examples. But in none of these did we actually have to list out the actual orderings. We could count them without just listing them out. And sometimes these numbers can get really, really big, okay? So be careful when using factorials. These numbers, I will say, are huge and may cause calculation errors on your computer/calculator. So if for some reason your calculator says error, that's basically saying, no thank you, it's too big, I'm not dealing with it. But we'll not worry about that right now. Okay, so let's move on to the next video.